Good morning to Kanav. Good afternoon to Aritra. Panel on the second revolution in quantum computing world. We opened the session with a introductory session by Aritra on 9th of January this year. And at the outset, let me wish a very happy new year to everyone present here. And also, let's hope 2021 is much more better than the last year. We privileged to have today Dr. Dadwal, who is director of IIST. It's really good to have you here, sir. I will extend a very warm welcome to you. Our esteemed panelists, Dr. Kanav is my close very warm welcome to each one of you. Aritra, thank you so much for accepting the offer from our side, from IIST Alumni Association, to moderate this panel. Thank you so much. I welcome you to this panel discussion. And with these few words, let me invite Dr. Dadwal to please inaugurate this session with the address. Sir, your mic is mute.
Right. So we reinitialize. So good evening, my friends in India. And thank you, Prakhar, and good afternoon to you, hopefully. So today we are meeting, I think, 1 month after our convocation, which happened online. So last year, we learned the power of this online meeting. So the grave disruption, what we had in our life, so we used a disruptive technology to overcome. So that has a lesson for all of us. We also are now in India in a very exciting phase that the space ecosystem has been, I would say, given a new direction and new opportunities. So now every week, either you see a private company, a startup has either tested a engine, and more importantly, I think in less than a month from now, a startup would have launched a hyperspectral space mission, a satellite called Anand by the Pixel Technologies. So where does this leave all IIST family members? We have looked at a limited sort of horizon, but I know we have very, very, I would say, exciting exceptions from the very important startups, from Rocketeer to SatSure to CellProp, to so many things which our students have done. We also have now this year, the last year, established a Space Technology Innovation and Incubation Center, STIIC, and the first company which is building robotic NDT type of setups has already started functioning. But today, what we are here is to really prepare us for a very big unknown, that is quantum science and technology. I'm sure quantum science and technology will literally ask us to relearn many things, but it will open very large number of avenues, especially in the space technology. So the quantum sensors and precision measurement, whether it is positioning, navigation, timing, and very, very precise sensors for gravimetry, magnetometer. So whatever have been the limits of accuracy achieved, accuracy and precision, they would be very easily breached. The second area, of course, would be the quantum computation. So the algorithms and applications, I'm sure there would be very large number of challenges and opportunities. Another area would be the entanglement distribution. So sensor arrays, interferometry. See, the interferometry has already in the space technology allowed us to look at millimeter scale changes in the geodynamics and also visualize, terrain movement. But when applied in quantum science, I think we will be making very, very precise measurements and really understand this dynamic Earth. And of course, there will be the quantum enabled classical technology, something like single photon source detectors, quantum limited amplifiers. So while the space agencies are now working out a very important strategy, which is either in form of platforms and environment for advancing the quantum sensors. They're also developing computing test beds and putting algorithms. The distributed entanglement for interferometry, very, very long baseline, is another area. So for the very long baseline interferometry, I can share a discussion what we are having with IIT Kanpur. IIT Kanpur have just now, with DST funds, established a National Center for Geodesy. So we are, IIST would be a part of their sort of network, what they will do. And currently we are in discussion with them that very long baseline interferometry antennas, which would actually be done with the help of Space Application Center, we could set up at the Ponmudi, because the Ponmudi has an advantage that you really have the satellite laser ranging. So if you put a satellite laser ranging and for geodesy interferometry antenna, so this co-hosting can give additional strength and computation of large number of things for orbit dynamics, as well as for precisely knowing the orbits of our satellites. But coming back to the QST, the deep space communication would be another possible areas. And in that context, I would like to say that IIST is trying to work on some of the CubeSats. Although we have an approved program of putting our sensors on the MOM-2 and Venus mission, but I think the IIST students and faculty would really design the new mission with CubeSats. So I would like to compliment the entire alumni association, family, and all my friends, because since we inaugurated this, you have really taken this continued learning, like a duck takes to water. So I am really very, very much sort of satisfied that maybe we delayed it, but we brought in this grouping and we could sort of put this in place at a very appropriate time. From the IIST point of view, we would really like to look at this continued relationship with the alumni and walk with them in whatever they wish to achieve. And as far as the institute is concerned, so we have had discussions with your teachers and my colleagues, especially Narayan Murthy, Dr. Solomon, Sudesh, Murugesh, also Dr. Ashok Kumar, the new faculty who has joined. He is really setting up one setup. So I believe they also would be drawing up some course either on quantum information. So I'm happy to see Professor Solomon is here, or quantum computing. I leave it on them, how they would really introduce these disciplines and subjects in the IIST curricula. But I'm sure this would happen soon. So let me inaugurate the second, or maybe the phase, I won't say the last phase, because as the time proceeds, there would be many such meetings in this area. Let me compliment the entire Alumni Association executive. Also compliment all the members on a Saturday evening who have joined, and also thank the co-hosts, including Aritra Sarkar, who is here. So use this opportunity and spend a very fruitful evening. I'm sure we all will be benefited professionally, and also this will help us in keeping that bond of the IIST alumni live and ticking. And thank you very much for making me part of this program. Thanks once again, and best wishes to all of you.
Thank you so much, sir, for that address. And it is actually your. We are always thankful to you for the support you have shown us to Alumni Association. And thank you for all the blessings. So with this, let's start the key agenda of today, the panel discussion. And for that, we have Aritra Sarkar who will take it forward from here. So Aritra, over to you. Please go ahead.
Thank you, Prakhar. And thanks a lot, Dadwal sir, for kickstarting today's discussion. Firstly, I want to welcome all the participants here today. Thank you for joining. Humanity's fundamental curiosity has given birth to science long ago, and it is this curiosity that has driven us forward this far. And today's panel discussion is just another witness to that very drive. I'm very honored to have with us an amazing panel today. But before I go in and present the panel to you, just a reminder that you can type in the questions in the chat. And if you want to ask the question to someone specific, just mention that in the chat as well, so that we can take them up later when we go into the question and answer session. Let me briefly introduce the panel as we have here today. I know that I'll not do full justice to their illustrious career, but it would give us, let's say, more room to hear from them about their own work. We have with us Dr. Kanav Setia, a young quantum researcher, as I would say. So he did his BTech in aerospace engineering from IIST, and then he pursued a PhD in physics from Dartmouth College in the US. And that was on efficient quantum algorithms for solving quantum chemistry problems. He is also one of the earliest contributors to Open Fermion, which is Google's quantum computing repository. And that's where I first got to know that kind of works on quantum computing as well. So he had also worked with IBM on some quantum algorithms, and right now he is the CEO of QBraid, a quantum computing startup, and we'll hear more about it while we have the discussion more. We also have with us Dr. Solomon Ivan, who is an associate professor at the Department of Physics at IIST. He did his master's from IIT Madras and a PhD in theoretical physics from IMSC Chennai. At IST, he teaches the course on quantum information theory and, of course, a lot of other courses on optics and quantum mechanics. He is known, well, I didn't study physics at IIST, but he is known throughout the IIST community as a remarkable teacher with an innate ability to explain complex ideas with simplicity, and that's like very much needed in the field of quantum computing, I believe. He's also a very renowned researcher in the field of entanglement and non-classicality in continuous variable quantum systems. And he follows both a theoretical and an experimental approach towards this. And finally, we are honored to have with us Dr. Urbasi Sinha. She is a professor in Light and Matter Physics Group at RRI, the Raman Research Institute at Bangalore. She joined RRI in 2012, and right now she's heading the Quantum Information and Computing Group, the Quick Lab. And the Quick Lab works on multiple different topics, as I learned from the website. And there's the topic of quantum computing, quantum communication, and also quantum sensors. She's also an associate faculty member at IQC, the Institute of Quantum Computing, one of the best places to study quantum computing in the world at University of Waterloo, and also the Center for Quantum Information and Quantum Control at Toronto. She is heading India's first project on satellite-based secure quantum communication, the QUEST program. And like she got a lot of honors recently by winning the Asian Scientist, like Asia's top 100 scientists by the Asian Scientist of the Year 2019. So let's start today's discussion. Like Dr. Urbasi has been in this field for a very long time, and she's really at the top of the ladder of experience among the ones who are over here today. So sitting atop this ladder of experience from this vantage point, how do you see the landscape change in the last 10 years in quantum computing? Where earlier, let's say 10 years back, most of the discussions were like limited to quantum mechanical phenomena being tested in theory or in labs. But right now we see a shift towards application. So how exactly why or how did this transformation happen in this last 10 or 15 years?
So thanks a lot, Arithro, for this very kind introduction. Can you hear me well? Yeah. Okay. Yeah. So yeah, that's a great question to begin with. So you are interested in the quantum computing aspect of it to begin with. So what is the change that has happened in the last 10 years in computing?
Well, quantum, like we were discussing the last time, that the quantum revolution is more about controlling quantum technologies. And like quantum computing may be one of the applications of it, but of course there are other applications in sensing and communication as well. So in general, how did it change from the books to the experimental labs?
Yeah, the change has been remarkable. So because I joined around 10 years back, I mean, roughly 10 years back is when I started the lab here. And at that time, actually, there was a lot of skepticism regarding the future of this field and so on. And it was like, not in our lifetime. We are not going to have a quantum computer which will be of any use in our lifetime. That's the kind of skepticism I joined in, right? And so then, of course, the change from that to today being, we are talking about a national mission on quantum technologies. I don't think I have seen as such, I don't think any field has seen that kind of a remarkable change in such a short time span. And of course, I think we owe this to the fact that over the last several decades globally, now we are talking, of course, from a global landscape, right? Not just from an Indian perspective. And so globally, we have had a lot of demonstrations which have actually been, successful in proving that this is something which can be done. So in the first few decades, it was more about controlling the quantum systems, as you rightly said, the various properties, whether it's entanglement, superposition, and so on. But then came these qubits, and then the numbers started increasing. And so, of course, with this quantum supremacy that we achieved, with the 50 and then, of course, the numbers which are in that range. I think now it is like, so people are people and people who matter. I mean, all of us are the people category, and then there are the people who matter. I think we all matter, but then it's more the people who fund stuff for us. They are starting to believe that, this is not going to take our second generation's lifetime. And so the progress has not been linear. It is because, I think it's an amalgamation of physics, engineering, computer science, everything, people coming together and making these contributions, these companies taking interest, like IBM, Google, and so on. And so I think now we are looking at a very thriving platform. And so quantum computing specifically is something which doesn't seem like science fiction. And with all these demonstrations and algorithms and so on, which I'm sure we'll discuss more. And I would like to add something about the communication aspect, because that is where we have actually seen this, the practicality even more so than the computing, because computing, we are still not error correct, we are not still at an error corrected level. We can discuss that later. But in communication, we actually had the satellite QKD-1 demonstration from a neighboring country with the satellite already up there. And that changed it dramatically from science fiction to science for me. So I have been trying to push satellite QKD project from 2013. And of course, the everything fell in place remarkably with that satellite achieving some level of success. And so I think that is the one which is even more dramatic, because actually we have had long distance quantum communication demonstrated between continents and so on. And so I don't think we know of any other area in science or technology which has seen this kind of a leap in terms of the faith that people have now attained in its possibilities, which were always there. People like us would always argue that it is something remarkable, but then I think now the faith is much more widespread and in our favor. So I would we can discuss further.
Yeah, so another question that I had in mind was it's safe to say that we are in the very early days of what's to come. So we are in the early days of quantum technologies. And you mentioned that you already knew that this is going to come, but it was always a question of when we will be able to control these quantum systems to the level that we want to.
Yeah.
So in the early stage of your career in the PhD, you were working on Josephson junction. So this was mostly the superconducting domain. And then later you changed to photonics.
That's right.
And of course, we know that when it comes to building quantum computers, we still don't have the equivalent of a transistor. We are working, many different labs in the world are working with multiple different parallel technologies. They're trying to see what works, what's less error corrected. So why did you find that photonics is more promising than superconducting?
No, I don't find that at all. So I don't know. You missed a little thing in between. So if you see the trajectory, so I have actually always been very interested in exploring new, platforms as and when I've gotten that opportunity. So in between, I also did a project with the paper industry to make paper whiter, which had nothing to do with superconductivity or photonics. So it's more about, developing this broad, which I was blessed to actually have the opportunity to do. And so now, of course, I find myself in an interesting situation, because I am very comfortable with devices, with nanotechnology, with superconductivity, and nanowires and so on, which I have worked on, solid state stuff in IQC. And then, of course, the one thing that I wanted to add to the repertoire was actually photons, because communication is something that has always been interesting to me, and I don't think we can beat photons in terms of their ability to communicate without decohering. So then, in some sense, as you rightly say, we don't really know what is going to be the ultimate technology. So it's going to be some sort of a hybrid, is an assumption. And at the moment, if you have been following, we do have this very new work from this boson sampling perspective, which is an all photonic one, right? And so indeed, it is unfair to say that, because IBM and Google, they have actually chosen the superconducting platform, that doesn't mean that that is going to be the final. Because think about it, if we really want this happening in our daily lives, we don't want a dilution refrigerator following us around. So, so then photons is a way in which we can actually do things in room temperature, at room temperature. So I think it is very important that we have some exposure to different areas, and then, find ourselves in a position to contribute more meaningfully in a holistic way. So that is the idea. It's not like I think photons are better or anything. It's just that they're different and have their own advantages, which I have now been exploring for a decade.
Right, indeed. So when it comes to photonics, I'm sure that they are better in quantum communication fields. When
Absolutely.
it comes to universal computation, I think superconducting is better. When it comes to scaling up the production, semiconducting, of course, we know how to print CMOS on chips. When it comes to memories, NV centers maybe, and error corrections, well, topological, whatever.
Well, you seem to have a very definite choice. Maybe you shouldn't already
We don't know
collected
yet.
this.
True, right?
You're
Yeah,
too young. Yeah. So
yeah.
one
Like
day, you never know. Yeah.
we never know, right? So, but like that's basically what different people are exploring. That's the reason we do
Absolutely.
not fix on one technology nowadays. So let's move on to Dr. Solomon, because you're also working in the photonics, in the quantum information processing field. And like, if there's one word to explain quantum mechanics, a lot of people will choose as counterintuitive. So there are a lot of things that you can do with respect to our intuition of classical world. And there are, of course, a lot of what's known as no-go theorems, like a lot of things that quantum mechanics doesn't allow you to do. So what do you find the most fascinating of them, and what do you find exploring that particular property for quantum technologies, whether it's computing or communication, as like what fascinates you the most in the world of quantum information processing?
Okay, so let me tell my perspective. So, see, for me, optics is not different from quantum mechanics. Okay, so optics is the mother of quantum mechanics. If you see the big names, Sommerfeld, anybody who worked in early quantum mechanics, you'll see that they worked in optics primarily. Then they moved on to, basically it's wave particle duality. Okay, so to me, whatever is there in quantum mechanics is already there in optics. Okay, there's nothing new, except one ingredient which I learned from my teacher, which is called measurement, or the collapse postate, quote unquote. Except for this, I think everything is there in optics. Any wave theory has a formalism. So if you know how to solve wave equations, you know how to evolve them, you know how to whatever. Everything else is there in wave mechanics. Okay, so there's nothing really new except for measurement, which is what is the key ingredient in whatever we are trying to do. For instance, in communication. So that is my perspective.
So that reminds me of a very quick question, like maybe philosophical, but what's your favorite interpretation of quantum mechanics?
I have not learned any interpretation. I just solved Sakurai. So first, I think in my understanding, you have to learn to solve, work with calculation. Interpretation is for philosophers to discuss. Physics fellows, we have to work. Okay. So I am not worried too much about interpreting things this way, that way. Something works or not. For example, you take optics, quantum optics or quantum sensing for that matter. We have a set of equations which we describe, you calculate things, solve things, but things happen in a lab. You have to put, nonlinear media, you have to put something to make it work, and then we interpret it using our calculations. You say that, okay, we have achieved what looks like, what we predicted through our calculation is indeed correct. Our understanding is indeed correct. That's the picture I take. For me, I'm not worried too much about, what is the philosophical implication or that sort of a thing.
Quantum mechanics being subjective, the relation in quantum mechanics and cubism. So let's move on to Dr. Kanav over here. So you have changed, let's say, your understanding from the very big, the world of astronomy and aerospace engineering, to that of the small. What was that transition for you? Like, did you face some kind of a barrier to entry, not coming from a physics background, or did you find like all the different open source tools there? You found it easy to go into this field?
Yeah, of course. It was absolutely brutal, to be honest. my first year. Can you hear me? Can you guys hear me?
Yeah.
Cool. So yeah, the first year of the grad school was absolutely brutal, and I kept asking, how did they admit me here? Like, why did they give me admission? I don't fit in here. But yeah, but one thing that I really loved was physics, so that just kept me going, and it just gets easier with the time. So one thing I would say is, after my BTech, I joined SCL for 4 years, Semiconductor Laboratory in Chandigarh. And that's where it did take a lot of courses on edX, Coursera. So my math was decent strong. I had taken a couple of physics courses, and all props to Dartmouth Physics Department. Like the atmosphere, the environment is very collaborative, and they're very supportive. So if you're struggling, you would get like enormous support. So that's what I got. First year was hard, but then it gets much easier. And yeah.
So you worked on like the Ionic quantum simulation.
Yeah.
Physicist, I don't understand the full thing, the full term, but is that
Yeah.
the same thing as what Feynman originally dreamed of simulating a quantum system, which is like very difficult to do on a classical computer? And like, how do you go
Yeah.
about it?
Yeah, so the answer is yes. The fermionic simulation was one of the first things that prompted Feynman to actually propose quantum computing. And it was actually so the idea for using a controllable quantum system to solve such equations was by Feynman, and there was another guy, I think Yuri something. Yuri Manin, thank you. Yeah, so they both together proposed it, but the idea that quantum simulation in general scales exponentially on classical computers was sort of hinted by even Dirac himself, where when you write down equations for indistinguishable particles, and then you see the complexity grow. And at one point, I think he himself wrote that we have all the equations, it's just like they get too complicated. And so that's where in 1980s or something, Feynman proposed, hey, why not build a controllable system to which you'll be able to map the system you want to study. And one of the doubts he himself had was actually fermionic system. He said, like, I could see how bosonic systems would get mapped to these controllable systems, but I doubt that can be done by done for fermionic systems. And it was actually a mechanical engineer or a physicist named Seth Lloyd at MIT, who, along with his student, proved that this could also be done with fermionic systems. And to answer your second part, how do you go about it? So fermionic systems are the systems consisting of electrons, protons, so basically all the atoms and molecules. So if you want to study them, then you write down their equations, you write down Schrodinger's equation, and yeah, and then you there's a whole long process. I could do a talk, but the very succinct answer is you can't figure out a way to map those to qubits, and which was actually one of the research areas that I worked on. My whole PhD thesis was about coming up with a new mapping with which you would map the fermionic system to a system of qubits. And then you can use something like, there are various algorithms available, like variational quantum eigensolver, phase estimation algorithms that you can use on top of these mappings to learn more about the system.
Thank you, Dr. Kanav, and we'll come back to the open fermion again after some time. But let's move back to Dr. Solomon again. And so as Dr. Urbasi was saying, that there are also multiple different technologies by which to explore quantum computation. But in general, like the computing model can also be different. So we have, let's say, the quantum annealer, which is based on the adiabatic quantum computing model. Also, we have like the conventional models using qubits, but of course, we also have the continuous variable quantum computing. So that's also something that you have worked on in the past and presently also researching. So can you tell us, because like in the last in the introductory lecture, we were mostly talking about qubits, which are discrete states and two variable states. And like how different, how is it, how does continuous variable quantum computing work? And how do you develop, what kind of applications is it good for? How do you program applications in it?
Okay, so see, let me give my answer in this manner. So, see, we have something called, okay, you learned the formal qubit, what we call as a formally as a qubit in two-level system, you know, the formalism part. But then there is the other thing, which is called a simulator. For example, something can mimic something else. For example, polarization, state of polarization in paraxial wave optics is equivalent to a qubit. Okay. Nothing more. You call it Poincare sphere there, you call it block sphere here. There's no difference basically. The math is the same. So, do you want to call a state of polarization as a qubit? Okay, fine. So now what I find in literature is a lot of things going on. What people call as quantum simulator. So you take your desired quantum system, you construct something that mimics it and also reproduces all, you know, to very good level of accuracy the original system's physics basically. So yeah, so I guess that's what. So continuous variable is not very different from you know, it is wave. Basically, paraxial wave optics is continuous variable in a sense. So if you want to map it to a qubit, you can actually by looking at particular subspaces, for instance. Right? Looking at a system appropriately, you can view it as this or that, depend on the context. Which degree of freedom are you looking at? Okay.
So I'm a bit confused over here. So like, let's say if you have a qubit, you have like mathematically, you have like a superposition of two states. So
yeah, so for instance, so you take a harmonic oscillator, you somehow you're able to only access the ground state and the first excited state, say. Then basically you have quote unquote a qubit. If you're only addressing those two states. Two-level atoms, for example, an atom is not two-level. To say, you know, it is, you know, you solve the hydrogen atom equation, it is a billion levels maybe, you know, it's a continuum. Some places it's in a discrete and then it becomes a continuum later. But if you're accessing two levels, then you say, okay, I've made a qubit effectively by addressing these two levels. Okay, so in that sense, but if I want to access something more, maybe I perturb the system with some other potential and then I get more levels accessed. There's more radiation coming in, then there's a third level access and so on.
So like, doesn't the control becomes more and more difficult as you access more and more states?
Yeah, it's very subjective. I mean, it depends on system. For example, which system are you worried about? You understand? So that's my understanding at least. Like you see this, you know, some places it's very easy, trivial almost. Some places people struggle, and you know, for the same mimicking thing, it's deemed as a great work. You understand? So
yeah, well, thank you. So like, I think there's some work by Dr. Urbasi where she is exploring Q-trits. So that's like and what's exactly the challenge and advantage over here? And let's say, as Dr. Solomon was saying, why didn't you go into, let's say, the Q-tetrads or whatever it's called, Q-quarts?
Yeah. So questions for me, right?
Yeah.
Yeah. Okay. Yeah. So, well, of course, that would be the idea, to actually scale it up further. So you can have two different approaches, as Solomon said, that, you know, you can always have a system which has many different levels. And then if you're accessing two of them, then it's a qubit, you know, an effective qubit. But then, of course, you have the opportunity to access other levels. And depending on your application, you do what you have to do. But then now, if you have an infinite dimensional system and then you kind of scale it, you know, just access two of them, then that is one way of doing it. That's like a top-down approach. But then the way we are, you know, developing our systems, it's a bottom-up approach. So we are actually going and adding one state as we go along. So at the moment, we are at the lowest level of complexity above a qubit, which is a Q-trit. So then, of course, the idea would be to scale this up to 4, 5, and so on. And of course, our system will not allow us to go beyond a certain point, but then we can have a change in the system. So, but why is it interesting? If that was your question as to why do we need to access, why are qubits interesting if qubits are already so popular? And And that, there are two answers to that, I would say. One is, of course, because qubits are already there for a larger number of years, I would say, and more work has gone into it. And there are different systems which present themselves as qubits with their degrees of freedom. So a lot of work has happened, and we have people here who are working on algorithms, and the quantum computers, quote unquote, that we currently have are all qubit based. So then, of course, as a researcher, as somebody who wants to do novel things, it is interesting to explore a system where it is not quite that advanced. And so what are going to be the universal set of gates for qubits and for my specific system? So there are many more open questions which I can, of course, address. And so that is, of course, interesting to me as somebody who's interested in the research aspect, not just, in the capacity building aspect of it. But then, of course, there are advantages also from the application point of view. So if you talk about quantum computing, then, we are talking about this 50 qubit register, which is very popular. We talk about 50. Why is 50 interesting? Because of 2 to the 50, right? And I'm sure you gave this explanations and all that in the talk that you, delivered last week or something. And so then, the 2 to the 50 and so on. But then if I now change it to 3 or 4 or 5, then the 50 drops. So the same level of, same complexity of Hilbert space I can kind of access with a larger dimensional system. And so then that is good, because it took us a long time to reach 50. And of course, that was the point. It took us a long time to get these 50 in a coherent superposition. And so if I can drop that exponent, then there is an obvious advantage. If I can do that controllably, and that is where the challenge lies, because it's not so straightforward to just scale up. You have to actually have individual access to each of these levels without any bias and all that. So there are challenges, which is what makes life interesting. But then that is the idea that, you can actually drop the exponent with higher dimensions. That's an obvious advantage. But in quantum communication, there are lots of theory work, and I'm sure Solomon is aware of them, where they tell you that, you actually have advantage in a higher key rate and lower error rate when you go to QKD, for instance, in higher dimension. And so there's a lot of theory work which exists. So it will be interesting to actually see how much pans out when you actually have a system where you're developing this experimentally. So so I think both ways there is an advantage from a research point of view as well as from the application point of view.
Indeed. So let's say if you have 50 qubits on a 50 qubits, then you'd have 3 to the power of 50. That's
right. That is, of course,
bigger than 2 to the power 50, indeed. So that's,
please.
Sorry. Yeah,
no, go
so
on.
that, let's say, sets the stage for moving into quantum communication. So that's also something we would love to discuss today with you. So you're working on satellite space or free space QKD.
Mm-hmm.
And is the promise of securing a quantum channel with quantum information, is it mostly to prevent it from another quantum algorithm like Shor's factorization or a man-in-the-middle attack, a normal classical one? But what is the thread? Why do you want to move from a normal channel to a classic quantum channel?
Yeah, of course. So there we don't even have to worry about whether it's free space or fiber or satellite or whatever. So you're asking a much more fundamental question as to why we need to do QKD. I mean, what is the purpose of working with quantum key distribution? And of course, there, you have already answered it to a certain extent. So we have these popular ways in which we are securing information now, which is, of course, the basis of what we call cryptography, right? So you have something, you encrypt it in a key, and then the receiver also has the key, and then that guy can decrypt it, and then the information is secure between you and me. And so that is the idea of cryptography. But then having said that, the most important part of cryptography is this key distribution. So when you're doing this key distribution, you have to ensure that, for instance, Solomon doesn't also have access to the key, because in this case, he is an adversary, right? And so then I don't want an adversary to actually gain the information that you and I want to communicate. And that is important when it is something of a strategic nature, whether it is you are the bank and I am, your customer, I want to give you my details, the credit card, I'm buying something. Defense, there are many, even the electoral polling system. So if I vote for party A and I want that vote to be registered for that party. And now, of course, it is the most interesting discussion we could have regarding electoral polling. So then, having said that, these are all examples of strategic communication and where security matters, right? And so I would like to ensure that the method by which I'm making things secure is future secure. So something that I'm doing today, it should not be vulnerable to something that comes up 10 years, 15 years down the line and can break it. And so then comes this aspect of the Shor's algorithm, as you said. So many of our public key protocols like the RSA or discrete log, and there are many examples, which are based on the mathematical hardness of a problem. For instance, the RSA is based on the factorization problem. And so today, the factorization of a certain number of bit numbers cannot be done within a certain time frame by a classical computer, the best one. So it will take the age of the universe, as we like to say. But then if 10 years down the line, somebody like you, who clearly is very clever, comes up with an algorithm which breaks factorization, there is no, what should I say, proof that factorization is unbreakable. It's just not been done. So that is the kind of algorithmic breakthrough which can happen. And then, of course, the quantum computer itself will run Shor's algorithm, which actually has already, made the hardness class of the factorization different from what it currently is. And so these are all threats which are either already there or are looming up, from which we need to protect the security of our information. So we need a method of doing this which is future secure. So whatever I'm doing today should not suddenly be vulnerable 10 years down the line. And so my progeny should not suddenly find themselves penniless because all my money is now gone to a third party, right? So this is the kind of thing. And so that is why we need, and the quantum computer itself poses a threat here, which is unfortunate because it has many, many advantages as well. But this is one of the things it will also run inadvertently. And so we need to come up with a solution which is also based on the laws of quantum mechanics. And that is where your quantum key distribution comes in, where we actually check out the, mathematical hardness aspect and use quantum mechanics to secure the information, whether it is uncertainty principle or entanglement and so on. And so that is why you need a key distribution based on quantum. And that is what is quantum key distribution, which is basically the quantum part of quantum communication. Because otherwise the cryptography, the encryption, decryption is pretty classical. And so that is the answer to I think your question was about what is necessary. So free space, I don't know what your question was really. Yeah. And I have a noise. Is that from you? Or is it me? Let me mute.
Yeah.
So it's from you. Yeah, okay.
So thanks for that explanation. And let's break it down. Like, we are playing around with national security over here. But
are we? I hope not.
We don't know. Like, that depends on how early we have quantum computers, right? So, but as you said, like, there's like two parts to it. One, you have a quantum computer, and then you can break down the classical cryptographic system. And in the second case, you do not have a quantum computer yet. You want to be future proof, like you want to be future secure. Right. So that's like somebody who copies and stores the classical information today, in the future won't be able to hack it when quantum computer comes up. So it's like,
or any other algorithmic breakthrough.
Yeah. So like, well, like coming from classical complexity background, like it's most of the people know that maybe Shor's like factorization will not be NP complete, or like not be in P, the polynomial time algorithm. But of course, there are other classical algorithms as well, which do not have a way of breaking yet, like code-based or lattice-based cryptography. What do you think of those kind of approaches?
I wouldn't be the right person to answer about things that I'm not working on. So, I'm actually working on quantum key distribution. I can tell you why that's interesting. I think Kanav should be the person to answer this question, because he seems to me the most complex in this group, complexity-wise.
One further question from you, like one further answer. So I was watching a lecture by Peter Shor himself, and like he says that in the NISQ era, in the noisy intermediate scale quantum era, like Shor's algorithm is pretty much a far shot. So it's not going to happen in the 5 to 10 years down the line. Whereas if you look at QKD, you don't need a lot of qubits. You can pretty easily implement them. And even in the Netherlands, where I'm doing my PhD, KPN, the national telecom company, is trying to improve, like overhaul their networks to a quantum secure one. So, like, do you think like we are preparing too far ahead, whereas the quantum computing progress is lacking?
No, absolutely
far behind?
No, I don't think that at all. So first of all, I would like to correct the second part of your thing. I mean, if I may, it's not about needing less number of qubits. QKD, actually, each photon is a single qubit. So it's not, you don't need, so it's one at a time, right? So each of them is carrying one bit of information. And so then in some sense, the number of qubits is not quite a relevant aspect in the QKD discussion. But then having said that, when Peter Shor would say that, in the 5 to 10 years, he doesn't see his algorithm being a problem. Well, of course, that is where, of course, the first part of our discussion comes in, that, the rate at which the quantum computers are actually adding qubits to their repertoire is much higher than what we perhaps expected even 10 years earlier, right? So then now, of course, comes the point that indeed we only have 50 or let's say 75 qubit processors is kind of what we discussed. But then having said that, and in fact, we are not doing slides, but then it will take some, thousands of qubits in order to run Shor's algorithm to the level that it would be a threat to this. But then that doesn't mean that, we are not going to reach there in a much shorter time scale than what we would have thought even 2 years ago. I mean, so in that sense, I think in 10 years, we should definitely see ourselves reach that. Whether they will be error corrected is the important aspect, and I don't think that will happen. I think the fault tolerant ones will be still smaller number of qubits, but then I don't really see why that would be a bottleneck to running Shor's algorithm. Shor's algorithm has already been demonstrated, as you know. So 15, 21, every time there is a number, we hear about it, right? So then it is, if we have that processor which has that large number, then it shouldn't be difficult to implement that algorithm. So when this is actually in fact, this is something I'm saying for several years now. So it's almost like you are a funding agency and I'm defending my proposal. But then that is not the point. The point is that, you can't wait for something to become a threat and then start working on the solution. It's a little, it's a little, what is the professional word? It's a little silly is what I want to say, really. Because, if you actually have already done all this, then in 10, 15 years, there is no threat. Nobody even knew. The children who are not born today wouldn't even know that there was going to be this threat from something called Shor's algorithm. So that is what it is, right? You don't want to wait and, okay, now we have 1,000 qubits. Now let's start developing QKD. That's a bit, naive. And of course, there is also post-quantum. I mean, I'm sure you will discuss that at some point. It's QKD is not perhaps the only way of doing this. There are also things called post-quantum algorithms, which are classical and nothing quantum about them. And that is an alternative approach. And so there are different mitigation strategies which should be done now so that there is no threat. And so I wouldn't agree if Peter actually said that, I don't know. I mean, once he develops his algorithm, then he's free to actually say that it's not useful. But then, I don't think he would mean it that seriously. That it, even in his lifetime, I'm sure it would be very useful.
Indeed. Like I would say that myself, that naive, silly is a better word than naive in this case.
Yeah, I just, we are going to have this uploaded on YouTube, so I can't use words which I would use in my team. Yeah. So
let's move on to Dr. Solomon over here. And so from quantum communication, you're also working on the field of quantum radars, which like a lot of audience over here would not have any idea what that is. So what exactly is the quantum part in a quantum radar, and how is it better than, let's say, a classical version of it?
Yeah, I am as naive as you are. I am also hearing this for the past few months or probably a year. Yeah, but what I understand is, okay, my colleague Ashok is here. Is Ashok? Ashok? Ashok Kumar? He's not unmuting. Yeah, so what I understand from hearsay is that, you can do better. It's like, it looks like promise to me. It's a promise. I'm not sure if, people barely what papers I've read, 1 meter they have demonstrated something, half meter they have demonstrated something. Real world is little away. I'm not sure, but whatever reviews I've read in the recent past, they suggest that there are a lot of bottlenecks. The concept is grand, it looks nice. There's a lot of promise, but in practice, achieving it is, as Urbasi already pointed out, that you don't carry your refrigerator, whatever that is, around to do your stuff. There are things.
Right. So yeah.
Understand? So to
Yeah, not asking from an experimental point of view, but what exactly is a quantum radar?
see, the question is, I don't know. 2016, there was a paper by Shapiro and Pirantola, if I'm correct. So what they claimed in the paper is something may not have entanglement, okay, but you can have signal to noise ratio. If I understand vaguely their key result of the paper, signal to noise ratio is still enhanced if you use quote unquote quantum that is not entangled. So if you have lost all the entanglement is broken, still you could have a signal to noise ratio gain. Which means, if in real world stuff, like if you want to detect something, maybe there's a very, very weak signal, still you are able to get the signature of that signal. So in that sense, it's a promise. Okay. But actual achieving it is I don't know, means the literature itself is little vague, or people claim various things in various places. So I'm not really sure of what they actually what they actually saying, meaning what are they claiming.
Okay.
So it's a nice word, it's a good thing, but okay, these things are there, theoretical predictions are there, but how do we do it in practice?
So is that the core of the collaboration that's going on between IIST and SAC, or is that on something else?
Yeah.
So maybe you should answer.
Yeah, I lost the yeah. I'm here actually. So yeah, the main idea is the SAC started that some project called Quantum Radar, and of course they were inspired by the earlier work from like MIT and other groups. So what we have seen recently is there was a paper from like a Austrian and Canadian group that for the radar technologies, you need to have a microwave photon actually, or radar basically works on the microwave domain actually. So what they were doing, basically they have generated or they have demonstrated what Solomon already told, like within lab in 1 meter that protocol works. But the main challenge will be whatever the technique they use, something called quantum illumination, that works extremely lossy environment or noisy environment. Actually, when you have a lot of losses, then only you can get quantum advantages in that actually. It looks like a kind of contradictory what we think, but there in those domains, still you can get quantum benefit. But still, the thing is, now the main challenge in those radar technologies is we don't have like efficient source of microwave photons actually. So what SAC has proposed recently, or I'm also part of that. So they just want to get a kind of lab model or prototype of can we demonstrate this kind of thing in the lab at least, although people have demonstrated already, but they just want to have a lab model where we can demonstrate first in the optical domain, and then they will go for the microwave domain actually. That's the status actually. The bottom line is just we want to put our hands in those kind of technologies. That's what the current status is.
Thank you. Yeah, that's perfect to start early, as Dr. Urbasi was saying. Yeah, so let's move on to Dr. Kanav again. So you are like right now a co-founder of a startup, and you have recently been funded as well, I believe. So the model of a venture that we have is somebody who wants to get a return on investment in a few years, say 1 or 2 years, right?
Wait. You broke up for a little bit. Could you go like 20 seconds back?
So you are like the co-founder of a startup, the CubeRay, and I believe you recently got funded as well. So like the model of a venture capitalist that most of us have in mind is somebody who wants to get a return on investment as soon as possible and within a few years. So how do you project the return on investment when you are pitching a quantum startup, and what's the model that you're following at Qubit?
Yeah. So first, we haven't gotten money from the venture capitalists yet. We have received funding from a couple of angel investors. And the model we've been pitching is, so we're not doing everything quantum. The way we are going about it is we want to create a platform which helps everyone in the learning and development area. So we're not developing new quantum algorithms. We're just making the access to the quantum technologies much easier. Right? For example, if you're a professor at a university and you want to start a quantum computing course, you come to our website, you would see that you would get access to quantum computing repositories, as well as a couple of courses already built. So you can get started. So from our end, we expect to generate revenue relatively soon, as long as the field doesn't go away. We should be making, so we're not depending on quantum, our business viable. So that's been the key point that most of the investors have been happy about. The other point I would say, yes, the traditional image of venture capitalist firms is they expect returns on their money within 7 years, but there are a lot of other venture capitalists who are able to take long shot. Like there's so many companies in Silicon Valley who invested in, let's say, Tesla, SpaceX, right? Something that took more than 10 or 15 years to get their returns on. So there's so many, and because of their success, there are just so many people starting to believe, you know what, hard things do take a long time to come to fruition. I'm sorry, I can't hear you.
The investment scenario in US and India.
I think your voice is really muffled. Can you go again?
The investment scenario in
I can't hear. Nope. Can you hear me?
Yes,
Can
we can hear you.
everybody else? Cool. For some reason, I can't hear
No,
Aritra.
neither can I. So, Aritra, you have a problem at your end, I think, the microphone.
I'll try now.
Yes. Yeah.
Yeah,
Yeah.
great. Yeah, so the question that I was asking is like the investment scenario in US and India is of course drastically different. Recently, we have a lot of funding from the Indian government in quantum computing on building a quantum processing unit, whereas in the US, you find investments all over the landscape of quantum computing. There's investment on like the development tools to build quantum computers, the compilers and the programming languages. There's investment, of course, on like all the big companies are invested in building the quantum processing units. And of course, as you said, like your company is also invested in the quantum education sector. So
Just clarify. Just to clarify, we're not just working on the educational sector. We are developing a lot of tools for the researchers as well. So if you come to our platform, you will get access to everything sandbox. So basically, we want to augment every researcher's ability to access these tools relatively fast without spending, let's say, a couple of months figuring out how these tools work and how to access them in the most efficient manner.
Okay, so quantum computer that's being developed, the quantum processor, let's say, that's being developed in India, like, can it be integrated with the tools that you are building? And like, if as long as I know how to program a quantum algorithm with 4 qubits, I'll be able to run the algorithm on like via the platform that you have.
Yeah, absolutely. So that's basically the aim. For example, right now, you can definitely come to our platform, access IBM's quantum computer. We will be adding support for various other quantum computers, for example, from IonQ, Rigetti, And in the long run, we hope to also add support for Xanadu's photonic quantum computer. And there's another really amazing company in Silicon Valley called PsiQuantum. So they seem to be doing really great, and hopefully, when they bring their quantum computer online, we also hope to make those available as well. From our end, basically, we are solving the software part where we figure out how do you connect to the quantum computer. So there's like a lot of API stuff going on. So you as a researcher should just have to figure out how to build the quantum circuits. And then you shouldn't have to spend the time figuring out the software part. Okay, now how do I connect, or how do I make calls to various other quantum computers?
That's great. So I hope that Dr. Urbasi and Dr. Solomon will also use the tools that you're building in the future. So like Dr. Dadwal was talking about the quantum educational course that should be there in IIST and perhaps in every other institute in India as well. So there's a question for Dr. Solomon. And what do you think is like should be the curriculum? At what stage should quantum computing should be introduced? And what kind of courses do you think would benefit and prepare the students for the future to come?
So we are already teaching it. This has been part of the curriculum. Even before I joined, I think Murugesh has taught this course. Then when I joined, I started teaching it. And then when I was a grad student, I have learned it from some other professor. So it is there in the curriculum already. You have an elective in IIST. It's sometimes it is given as an institute elective, sometimes as a department elective. It is already there in place. But now, I don't know, Murthy has been, Professor Murthy, you're aware, right? Professor Narayana Murthy, he's very enthused about, he discusses very often about starting some new, a separate course, like we have in MTech in optical engineering or MTech in solid state technology. He says there should be a course completely dedicated to quantum information science. But I don't know. But otherwise, the things are in place already. Meaning the courses we have, quantum optical communication courses there, quantum computation, some syllabus is there. So we have then quantum information theory. It's all taught already there in the system. So maybe the avionics and aerospace students didn't have that thing.
Unfortunately, both me and Dr.
Yeah, maybe for in that way, I think the way we introduce mechanics and electrodynamics as a core course for our BTech, for all BTechs, I think quantum mechanics should be made universal for everybody, independent whether he's an aerospace engineer or in IIT. When I was doing my MSc there was a course called quantum mechanics for engineers. It was just dedicated, the same teacher teaches the same course. For us, we call it Quantum Mechanics 1. For them, it is called Quantum Mechanics for Engineers. So maybe that kind of a thing may be a good start. Meaning, it is there in, things are there already where everybody is learning the course. There's nothing new or mysterious about it. It's only the, now that a lot of money has come in, I think people are talking a lot about, starting this course or that course. But otherwise, the courses themselves have existed. The moment Schrodinger wrote down, entanglement is as old as Schrodinger. You understand? So I'm not clear when you say that there's curriculum. It's already there in the curriculum.
Like if we look at IQC in Canada, like they are one of the few like master's program and math program dedicated to quantum information. And like, I believe that in quantum computing, you need a lot of interdisciplinary knowledge. You need people from
that's true. Yeah. So that was what is Professor Murthy's idea. He has been going around discussing with everybody nowadays. Like he comes to my room, Ashok's room. Probably I don't know how many rooms he has visited, giving putting seed of this idea into people's minds. So I think it might happen. I'm not sure. So.
Well, that's great. Like we would love to see the seed bloom into a flower soon. We'll move on to the questions that we already have from the audience. So the question, like as I said, is normally directed to one of the panelists. So I'll just read out the question, or like I'll ask to unmute whoever like the participant's name. So we have a couple of questions from Vibhuti over here, and I'll like ask him to unmute.
Hi, thank you, Aritra.
Yeah, I believe you have a couple of questions for all the panelists. You can go ahead with them.
I wanted to ask Professor Urbasi about the idea of using multiple degrees of freedom, or does he envisage a time wherein there may be many satellites using different modes of or different degrees of freedom? For example, working on the discrete version, one operating on the continuous version, other on the optical, this angular momentum thing. So, is the idea quite far-fetched?
No, it's not a far-fetched thing. So then, in fact, there are. I mean, of course, we are now talking globally. So there is equal, impetus given to CV, QKD as well as DV. So DV is discrete variable, CV is continuous variable, and so then there are, of course, also attempts. I mean, as you know, the satellite QKD. There's only one particular satellite which is out there, but then there are programs that different countries are following towards that, and so there are approaches where they are going the CV way. So Germany, for instance, has a particular group which is working on the CV aspects, and then another group which is working on DV. So then, indeed, I think we will see the merits and demerits of both in free space over longer distances in the next few years. And then, of course, whether there will be different satellites which will be doing different aspects, that one is a little bit, I would say it's our positive wishful thinking that we will have multiple satellites, which of course is the idea. But then if we are able to have at least one per country, that would be a good start. And then we would have the multiple ones. And in fact, we would envisage, inter-satellite communication as well. So it's not just about satellite to ground or ground to satellite. The satellites will also communicate with each other. And that is, of course, the bigger picture towards this global quantum communication network, where we will have, some satellites which are sort of accessing different countries, and then we have fibers, and yeah, so that is of course the future that you're talking about. But indeed, both are being researched by different countries.
Professor Urbasi, on that similar note,
yeah,
what are your thoughts on using platforms like unmanned aerial vehicles or balloons, which are not much in the atmospheric, like not higher in the atmospheric regime, however, to counteract this turbulence problem or dispersion or scattering mechanisms?
Yeah. No, it's of course it has already been done by other countries. We have had balloon experiments in QPD. We've had aircraft experiment. And so, in some sense, balloon is of course a good intermediate step, because of course even if we wish, it's not very straightforward to just have a satellite for testing. I mean, as you guys know, you are from ISRO, so you are aware that it takes a lot of effort to go towards a satellite-based QPD. So these are nice intermediate things which one can do, where we can actually have a difference between, say, we are doing the horizontal QKD now, right? So terrestrial QKD between two different, stations which are looking at each other horizontally, but then balloon gives you the option of looking up. And so then clearly, and also it has this undulating aspect to it, which is also a nice thing, because it kind of makes it a little more practical than something which is just stationary and waiting for you to communicate with. So yeah, so these are ideas which have been explored globally, and of course should continue being explored. I hope that answers the question.
Yes, sure.
Okay, yeah. Arutro, are you going to take this over? Or?
Yeah. So I believe Vibhuti, you had more questions, right, for Dr. Solomon as well?
Okay, so I was the subsequent one. So the question to Professor Solomon is that there are papers, so it seems quite counterintuitive, whereas in QKD, the decoherence effect leads to some deterioration in the link capacity and all, whereas for the quantum radar case, it is decoherence which manifests as a gain in the signal to noise ratio. So it seems quite So what are your thoughts on like where does this advantage in quantum radar comes from? Like
See,
where does it lie?
Vibhuti, see, it's all, what people make out of, the formalism is the same. Please understand one thing. It is our interpretation that makes, because we need to do verbal interpretation of what theory predicts. So, in my understanding, the gap is in our verbal interpretation of, the formalism. The formalism is in place. It is very watertight. Quantum information or quantum mechanics is very tight in, formulating the statements are well formulated. The questions are well formulated. It is our interpretation of the answer that makes it, looks fascinating, and, it gives rise to, so-called counterintuitive ideas or counterintuitive thought process. But whatever it has to say, it says. Okay. So you want to believe it is counterintuitive, then it is up to you. Okay. It is very subjective. The theory tells whatever it has to tell. You do a calculation in a particular manner, it gives you that answer. So I'm not sure what is counterintuitive about such a thing. Okay. You understand? Something is breaking entanglement, it breaks entanglement. So what? You understand? If I broke entanglement in this manner or that manner, the theory tells that if I did a calculation this way, I get this answer. So I'm not getting the counterintuition or, the confusion part. Does it answer your question?
So maybe not. I am still confused, but maybe I
I
have
think
to
you
read
discuss
more.
with me separately, Vibhuti. I think, yeah.
Sure.
Vibhuti, you also had a question for Dr. Setia as well.
Yeah. So this is a combined question to Dr. Sethi and Professor Urbasi. So how do you think the startup ecosystem of India in quantum technology is shaping up or will kind of shape up in future? And what should be the strategy of government or academic institutes for tapping in the large and sort of brilliant PhD output that comes from India in quantum information theory or quantum information fields?
Kanav going first as the startup person here.
Sure, I can go first. I was going to ask if you wanted to go first, but that's okay. So I can speak a little bit to the ecosystem in the US. So here, again, it's not very clear how the field is going to pan out. There's been a lot of progress, but there's a lot of skepticism as well. But here, there are a lot of venture capitalists who are okay funding something that's not completely figured out, and they are okay to take the risks. So that's where I would say it's a little easier to do it here, given that the technology itself is not figured out. The business part is another layer. Like, how do you build a business on top of something that's not there yet, right? So that's a little bit difficult. And if I'm being completely honest, I have no idea what the startup ecosystem, especially in quantum, looked like in India. The big problem in the United States that I realized a couple of years ago when I had worked on quantum algorithms for quantum chemistry. And so the initial reaction was, oh, let's just build a company which provides software for doing quantum chemistry, and then we'll make a business out of it. But then the idea was, okay, you wrote the algorithms, and I wrote the algorithms. Those are accessible in Qiskit and OpenFermion. But in the end, who would you sell it to, right? And so the initial reaction would be, oh yeah, pharma companies. But the important point is you don't have quantum computers that could run those algorithms. So you won't be solving any problems, or you won't be adding any value to the end users. So nobody's going to buy your algorithm for which there's no computer to run on, right? So these are important questions. So ultimately, we figured out a model where, hey, it doesn't matter whether you can solve quantum chemistry, you can always solve with one problem, where you make the field accessible to a large amount of people very easily. So we built a platform with few clicks in, you get access to Qiskit, Open Fermion, and all the technologies, along with the best tutorials that we think we spent like 6 months to 1 year building this version that even high schools can pick it up. So we've done like multiple programs with these high school students who run their own nonprofit organizations. So we've trained close to 1,000 students already. We are on track to train somewhere from 5,000 to 10,000 students in the United States in the field of quantum computing. So that's where we realize one of the things you have to do is bring more people in, bring more talent in, and hopefully we will make some money and fund our own operations. So eventually we could move on to developing software for quantum chemistry that ultimately will be used by pharma companies and so on.
Yeah, so I could pitch in a little bit about the startup situation in India. So, I mean, it's very interesting. So the startup situation in India was kind of non-existent a few years ago. And I think there has been a lot of boost to such a thing with the promise of resources. So, I mean, it is quite straightforward. I mean, so that is why, I think I echo Solomon here, who was saying this from a different perspective about coursework as well. So the promise of resources has really led to a lot of, new interest, renewed interest in quantum, which perhaps was not there before this promise, which we are all very well aware of, this national mission, which should be taking off shortly. And so there, of course, under this national mission, I'm a member of the committee which has drafted the document. And so in some sense, at least from our perspective, we've actually put in a lot of emphasis to, resources for R&D in, the research labs. And then there is the government sectors. I mean, like you guys are representing a bit of both. And then, of course, there is also the companies and the startups. So everything should be encouraged, because all said and done, unlike the US, it's, we are not quite, at the same level in terms of our developments in the technological domain of quantum. So we are, there are a few of us, a few labs which are there for a while, but then more and more have to happen before we have such an ecosystem. So we are, of course, going to have that in a few years' time, now that this promise of resources has happened. But then one thing that, it's I think, because now it's nascent, it's very new, this thing. So it is very important for us to know what the startup should be doing. So not every startup should be saying that, I want to make, a QKD system or a quantum computer, because that is not the only thing that you can do. The things we are really lacking in our country is actually things which enable these things to happen. Like, for instance, we would like a startup which works on lenses and mirrors, which produces them at an international level. Because we do have some companies which do that, but I'm sure Solomon is nodding because he agrees that they are not at that same level of precision as the companies which are our supermarkets, which are not here. So then, the startups, if they want to, be relevant to the field and also, nurture their interest in quantum, they should also think about being useful from the perspective of enabling this. Not everybody has to do the distribution. But then if you have fibers which are, very, very polarization maintaining, so perfect fibers, we don't need to go to US or Germany to buy them. So that is where this thing about indigenization will kick in. If we actually have FPGA chips which we can buy locally, if we, I'm talking from an optics thing, but FPGA, of course, is an electronics thing. It's available. It's useful for everything. So I think this is where we are lacking a little bit of imagination, at least from my, exposure to what we have seen over the last year or two. But I don't think that is going to remain for so long. I mean, once this thing kicks in, I'm sure there will be lots of people who will be starting things towards, these developments. Because otherwise, we are not going to become, at the risk of being cliched, but then this Atmanirbhar thing that we keep talking about, that is never going to happen if we are not going to become Atmanirbhar in the things which actually enable these computers or these distributions or sensors. And so that is where I believe we can really gain a lot. And of course, our production is somewhat cheaper. Usually in India, many things are, we are also cheap, like the manpower. We don't want to discuss salaries here, but then in some sense, we are aware that certain things are enabled somewhat less expensive manner than perhaps in our counterpart countries. So if we can actually develop things which are at international level, then we can start exporting them. We don't need to buy from Germany or the US or whatever. Right? So that is where I think we should spend some imagination in the startup system. Otherwise, we are going to just see these people who are very interested just because somebody has promised some resources, but then that interest, it's our moral responsibility to ensure that that interest is nurtured properly, because we have not started 50 years ago. And so we need to do things so that we are clever and then we can lead. And so there, where this cleverness cannot be just so Solomon will do our protocols for us, but then who will implement them? We still need to buy a fiber from, France. Then that's not a thing. So I think that is where we need to be more innovative. Yeah. Anyway, so there are quite a few startups now, at least on pen and paper. But what they are starting is something we need to watch.
So I'd like to add one thing.
Yeah.
IIST, is one place where it can happen because we have a course called MTech in Optical Engineering. This is very unique.
Okay.
I'm
That's
not
nice.
sure if any other department, even IIT Delhi, doesn't have an equivalent where we teach optical fabrication and testing as a separate specialized course.
That's great. Yeah. And this is what you need to then, encourage, because that is, people should be equally excited by that aspect. And not just the final product, because without this optical engineering, we are not going to really stand a chance if we have to compete, as a country.
Students indeed go to companies which manufacture lenses and
yes. And so they need to do a better mirror, so the mirror mount needs to be...
no, there are people, so let me tell you, Professor Urbasi, that there are people who are working in with Korean firms or Japanese firms. Our students have got placed. So
there you go. So now we need to retain them and have them work.
Yeah, no, they're placed in Bangalore. They're placed in Bangalore. But
I can imagine. But then how does that help, Solomon? They're placed in Bangalore working in a Korean... of course, it's great. That is how we will start. But then the startup shouldn't just be starting. We need to start also being based in Indian firms which actually have that as their mandate. So I think you have actually said exactly what I was trying to say. You've just, made the point even more, this thing that, there is also training happening in this, but then this needs to convert to everything happening here.
But Hallmark, for example, is not bad. Eh?
What, sorry?
Hallmark.
We can discuss that, of course, in something which is not on YouTube.
Okay.
Yes. Yeah, we need to be careful, no, Solomon? Yeah.
Thank you, Bibhuti, for inciting the discussion on the different scenario that we have in India and all the different technologies that we really need to develop before we have this technology being realized as a whole. So we are doing really good in terms of time. We are 1.5 hour panel discussion, which touched on many different domains. But I'll make the panelists go through one last question. And this is, let's say, from the articles that we see on popular media that quantum computing is here because the session is on quantum computing more specifically. So, and we know that predictions failed. And one of the popular internet joke was like Bill Gates predicted in 1981 that no one will need more than, let's say, 600 KBs of memory for a personal computer. So that's way off from what we have now. So let's talk about quantum advantage. And the thing that I'll ask all of the panelists over here is, what is their vision of quantum advantage, where a provable algorithm is demonstrated for information processing, not communication, let's say, on a quantum computer? When can we expect that? So is it already done? Is it less than 5 years? In a time period from 5 to 10 years, or it's 10 plus years away? So let's start with Dr. Kanav over here, since I believe you are the youngest and the most enthusiastic to see that happen as soon as possible.
So I will take objection to that. He may be the youngest, but then, enthusiasm is not inversely proportional to age. Yeah. Then please go, Kanav. Yes.
So let the course decide. Let's say, when does Dr. Kanav think?
I think
when we'll see quantum advantage?
No, I think Professor Sinha, you should go first. I
No,
mean,
no. It's always good to go last here because then I can say that I repeat what you have already said and I future is bright. So please.
yeah.
Bell the
So
cap.
I would say it's really non-trivial. Like one aspect is, okay, first you're gonna need like a fault-tolerant quantum computer, and okay, if that's there, then how do you build like algorithms? Theory part is one thing, coding part is another. So there's decent amount of theory part, and so even for the smallest molecule that you can actually simulate using the compute powers of classical computers, something, for example, simulating 30 or 40 qubits. Just setting up the coding part where you already know the theory part really well.
Let me just interrupt and like we discussed a lot of the challenges that is there, and the reason for this question is to sum up the challenge into a prediction on a single number that's less than 5 to 10 or 10 plus. That's going to like compress all the uncertainty that you think is there in the market today.
Okay.
And as I said, like it's bound to fail, but what's your shot?
I would say my hope is 5 years. If I'm being pragmatic, it's 10-ish years. Yeah, it could be 10 years before we see a perfect example where quantum computers are provably better, at least in quantum chemistry problems.
Okay, and where do you stand, Dr. Urbasi?
Oh, you go age. Solomon next.
Okay, yeah.
Yeah, my opinion is I'm not sure if, what is the advantage part is, again, very subjective. Because, the whole thing of, this quantum cryptography, for instance, is built on mistrust of one person on the other. The whole fact, you simply suspect the other fellow, that's why you want to protect. Probably, all this will get solved if, one can learn to trust the other fellow, without any suspicion. Okay, so
imagining, as I said, like the quantum definition
as an
is
academic,
very subjective.
Let me tell you, as an academic, I'm very fascinated by the fun part of it. Meaning, a lot of math and physics goes into writing a code or an algorithm, for instance. But for me, that's the end of that. After that, I find practically on my side, I find no use because basically the whole thing is about your basically man's selfishness and man's suspicion on the other. You want to protect your thing. If people were gentle and nice, all this is more on fun rather than actual whether we did this, whether we protected our bank, whether we locked our locker properly.
Yeah, so like cryptography need not be the only application, right? Like there can be other information processing application, and we are talking about quantum computing over here. That's what like I tried to clarify.
You look at why does China build supercomputers? Because you want to search. You want to search out who is whether if there's an attack. How do I search out and do I find the intruder? Can I search out the intruder? The whole thing is built on mistrust. That's why people keep on building bigger and bigger things just to protect your so-called secrecy or whatever, your secret files. So I find it sometimes very funny because sometimes when I write a sheet of paper, I write a calculation on a sheet of paper. Maybe after some days it goes to the dustbin. Nobody ever found it. The moment I load it into Google, share or somebody I shared, people read it, people try to steal it. I think part of the problem is is with us actually. I think many things will get solved if there's no requirement for it's nice actually. It's good to build things, but only up to that. Why are we in a race to okay, I built this, I got this, I factored 21, I factored some other number.
Yeah, so like as like moving on to Dr. Urbasi, like Dr. Solomon has very intelligently avoided taking the prediction.
Dr. Solomon has spoken like a true 70-year-old, which he isn't. So then, it just makes my life much easier, actually. So, I mean, now, first of all, he's proven your theorem wrong, that enthusiasm is inversely proportional to age. So then, I mean, Solomon, after we finish this discussion, please give me your credit card details and your wife's smoker details, because, you can trust me, right? So, I mean, so you are actually, I mean, on a more serious note, so of course, as Aritra has been saying, it's not just about the security part, but the security part is important because, all said and done, whether we like it or not, certain things are actually useful to a third party just because they are not meant for him or her. And so this is something we cannot take away. So we have to go ahead with securing ourselves. Otherwise, we would find ourselves in a very interesting situation. But then the quantum, it's not just only about that, right? So I think we are missing out on some other applications, which I think will definitely happen in a more promising way in the 5 to 10 year domain. And so we are, so think about, the falling ill. I mean, if we are falling ill and then we are having these scans which we are going through, whether it's an MRI and things like that. And so there, we are, of course, talking about using, imaging techniques, which are currently what we are, basing things on, which we won't get into. But then if, for instance, this imaging were to actually have this quantum advantage, which is what people like Ashok and all, people are working on, using entanglement towards actually getting better sensing, better imaging, then of course we would have these, obvious ramification in, our medicine. So we would be able to benefit from superior tools for, diagnostics. And then, of course, we can also have, kind of mention the simulator part. Then if we are able to use this well, then we may be able to design better drugs. So this is something which is actually much more in the near future than, let's say, the Shor's algorithm, which will be 4,000 qubits. But that's also not very far in the future. We already had that discussion. But then, so there are many things which we can envisage doing by using the what's so-called quantum advantage, where, of course, already there are demonstrations which are proof of principle, which need to now get converted. So this is where the startups would be very handy. People, to take interest. So, for instance, I know, but I can't divulge much. But then there is, this company called Schlumberger, which is one of the biggest oil companies in the world, right? And so they have actually lots of collaborations where they're trying to figure out better ways of tapping oil. So where exactly? So this sensor, which is going to tell me whether there is oil somewhere or not. And so there are means of doing that now. But if we make that through quantum, maybe through an NMR thing or some other process, then, we can have better ideas about where we can find things, something like oil. So there are many things actually which will gain tremendously by using our quantum techniques. And of course, one of them would be making things secure, but that's not going to be the beginning and end of the story. So we will have advantages. Even if we trust everyone, we cannot afford to say that we will also be healthy. And so, if the medical sector is going to gain from something, that nothing like it. If we have better drugs, nothing like it. So there are, we could go on and on with many different types of applications, which we haven't quite discussed in today's thing, where we've been very focused on the computer and what it can do. And of course, we know there are different algorithms which will be possible on a quantum computer, which won't happen in the same time frame as in the classical. And so the search is, of course, one of the common algorithms. But then we could use the search algorithm for better means than, mistrust. And I'm sure I don't need to get into those details. So I actually would definitely say that, there are so just by using certain things which are possible in quantum, which are not possible in classical. And I agree with Solomon that it's not because they're counterintuitive, it's because they are there. We know how to use them, and we also know how to calculate, so far as you are concerned, Solomon. But then both have to come in together, and we are going to have advantages in different sectors, not just in security, but security will be a big player here. And we have lots of actually privy to, I'm a part of this group which is working on standards for quantum technologies. So there's a part of a group constituted by the UN where we are actually trying to come up with international standards. Because if you say you have done something and I have done something, how do we know which is the one with the ISI mark? So we have to come up with similar standards in quantum. So there I'm privy to a lot of different areas which, we don't usually cover in these discussions. And so indeed, it's much more positive than, just about trust. But then having said that, we are an advanced race. We are, of course, in modern era, we have to look out for our interests, whether it is within the country, whether it is with other countries. And so we have to be prepared. Otherwise, of course, if we go in that ideal way, then Solomon, that discussion after our discussion has to happen, because I really will benefit from a little more money in the bank, right? So, so I mean, I could go on, but then Norithro, you can.
Thank you for your prediction of 5 to 10 years. I guess that's what you said. And that also gives me some happiness and self-promotion ground to say that I'm working on genomics algorithms in the field of medical science for quantum computing. And like, I personally believe that will impact, as Dr. Urbasi said, that searching need not be only for cryptographic keys. It can also be for drugs, whether you're fighting coronavirus or something else. So that also brings us to the close of this session, towards the close of this session. Thank you all the panelists for joining us today for this absolutely great discussions that we had on so many different topics. Like, this is, as Dr. Dadwal said, like, this is just the beginning of maybe like an educational journey towards understanding quantum computation and the need for learning. So 5 to 10 years away is like the perfect time to train yourself to understand this counterintuitive phenomena and to develop applications, to develop all the tools around it, so that we can really make this future happen in like 10 years from now. Thank you once again, and I'll give the mic back to the ISD Alumni Association for closing the session.
Yes. Thank you, Aritra, for curating such a wonderful discussion today. So on behalf of ISD-AA, I would like to extend a warm thank you to our panelists for their interesting answers to the questions that were asked and their insights into this exciting field. I would also like to extend a warm thank you to Director ISD for his continuous support in whatever we take up, and participants for joining us today. With this, we come to the end of today's session. So thank you all. Thank you very much.
Thank you. Thank you very much.
Thank you.